Good afternoon. I'm Lalit Pallegama, Chairman of Civil Engineering Section Committee of IESL. First of all, I would like to welcome you all to this seminar, rather I would like to say a lecture on non-destructive testing of concrete. Actually, this will be the last lecture, rather I must say a final event of Civil Engineering Section Committee of this year. As we all know, new session will be IESL session will be going to start from next month. Actually, today I think we all are very lucky to, as we all know, our resource person, Professor Priyan Dias, is expert on this subject. Early this year, we had one lecture from with him about compliance criteria of concrete, and at that time I have requested to conduct this one, and we have to appreciate to agree with that, and we all have to use maximum in this lecture. We all know who Professor Priyan Dias, but as custom, I will have to introduce him to this forum. Professor Priyan Dias has graduated from the University of Morocco and obtained a doctorate from Imperial College, London in 1986. As we all know, he was a senior professor of civil engineering at the University of Morocco. He has held Commonwealth and Fulbright research fellowships at the University of Bristol, UK, and Carnegie Mellon, USA, respectively. He is a fellow of Institute of Engineers Sri Lanka and the member of the Institute of Structural Engineers UK, of which is also the Sri Lanka representative of UK. He is also a member of the National Research Council, a fellow of Sri Lanka's National Academy of Sciences, and associate editor of the International Journal Civil Engineering and Environmental Systems. He has over 100 research publications to his credit, half of which in index international journals. One of his continuing research interests is in practice-based knowledge. That is about our resource person. As I said earlier, we all are very lucky to get this lecture from him. And before I invite Professor Priyan Dias, as a small notice, I think our mics, I think all listeners cannot speak during the lecture, but at the latter part of the lecture, you can raise your hands. Then we can arrange to unmute your mic if you have any clarification. Meantime, you can type in the chat box also. Then I hope Professor Priyan Dias will try to answer as much as possible. With that, I would like to invite Professor Priyan Dias to conduct this lecture. Over to you, sir.
Right. Thank you very much. Okay. So I just had a look at my slides. So I have a lot of slides. Oh, this is the wrong one, I think. Right. Okay, let's get started. I hope I am heard by everyone. Otherwise, please let me know. Right.
Yes, okay. Sir, we can.
Yeah. So, so this is a non-destructive testing and also assessment, meaning judging, right? Now, this is part of an overall appraisal of structures. Non-destructive testing means a concrete is already in the structure, right? And you can appraise at different stages also. Now, one very common thing is if the cube test failed, I think I mentioned this in my last lecture also, then you can look at the concrete in the structure. But if there are changes of use at midlife or also when the structure is very old, when you have to decide whether you're going to demolish it or not, then also you can do non-destructive testing, right? Now, there are two broad ways of doing this. One is to actually sample the structure and get material properties, which is what I'm focusing on today, and mostly with respect to concrete properties. Although those concrete properties may not be the most important, and I will tell you about that also. The other one is, of course, so then you take these material properties and then you check whether it is sufficient, or you can use those properties and do structural calculations. So that is sampling and testing the material properties. The other thing is to completely forget about the materials and do some kind of load testing, expected load, and then you see whether the structure is behaving okay. Now, this non-destructive testing requires a lot of interpretation, and it is not as like well accepted, or you sort of, there are sometimes disagreements, okay, compared to, for example, something like a cube test. But the problem is that the cube test actually tells us about the concrete that was delivered to the structure, right? If you want to find out about the concrete in the structure itself, then maybe if you take something like a core, then you will get a fairly direct idea about the in situ strength of the concrete. But even if you know about the in situ strength of the concrete, you do not have any idea about the design load capability, for example, of the structural member. So for that, of course, you need to do a load test. Now I am going to concentrate on this area, right? I'm going to concentrate on this area today. Right now, I think some of you who have heard my lectures might be familiar with this slide. Okay, first of all, I think I better, right, and then use the pointer. Okay. Now this is we are taking a simple slab. Those days we use grade 25 also, and steel FY is 460 with these bar diameters and spacing. And if all these parameters are at their design values, then let us say that moment of resistance is 14.35, and we divide that moment of resistance by 14.35 itself. So you say the moment of resistance ratio is unity, and all of the parameters are at these stated values. Now we can change one parameter at a time and see what happens to the moment of resistance ratio, right? So for example, if you think about the cube strength, instead of using 20, you make it half of that. That means 10 MPa, or you can make it double, that is 40 MPa, right? So you can see the cube strength has very little influence on the moment of resistance of a slab. On the other hand, if you change the bar diameter, that will have a huge effect on the moment of resistance of a slab, or the depth of the slab, right? Or the yield strength of the slab. Okay, so it is the steel properties mostly that govern the behavior of flexural members, especially slabs, right? Of course, where columns are concerned, then the concrete is much more important, because the concrete makes contributions of 69% and 53% as your reinforcement ratio goes from 1% to 2%, right? So then concrete becomes much more important, but much less for flexural members, right? So when we are doing non-destructive testing, we should look at some of these other things also, steel properties and properties like cover, because cover will tell us, especially for structures that are in mid-age or old age, it will tell us about the durability sort of conditions in those situations, right? So now there are different types of in situ tests, right? One is you have cores. Now the cores are like the sort of gold standard. I mean, because you're actually taking the concrete and testing the strength, which is mostly what we are worried about. But there are others such as the rebound hammer test and ultrasonic pulse velocity, which give us a correlation with strength. So they are indirect tests, right? So one way of doing it is to do some cores plus more indirect tests, right? So and you calibrate with the core test results. Now, sometimes you want, I mean, many contractors, want to get away, especially when the cube test fails, they want to get away with indirect tests alone. This, of course, I strongly advise against, but in a comparative mode is okay. In other words, if you know that there is a particular place in the slab where the concrete is satisfactory because the cube test has passed, and another part in the slab where the concrete is suspect because the cube test has not passed, then you can do a rebound test and you can compare statistically whether there is a significant difference. And I will go through that calculation. I think some of you, I don't know whether you all belong to those companies, sometimes they ask me to do this, right? Or if there are some existing cubes that have not been crushed yet, you can think about calibration with that. And in the last resort, which I don't generally use now, to use an existing correlation, because I'll tell you about some of the problems regarding those correlations, right? Okay, because I have mentioned it here, I will highlight later on, right? This gives you some idea. If you have a standard core like 100 or 150 millimeters, what is the level of reliability, right? So you need maybe 3 small cores to get the same reliability, 10 rebound hammer values, and like that, right? And even if you get it, what is the 95% confidence limit of the value that you get? These ones give you these kinds of numbers, right? Most of the time we don't use these, because what we do is we do make some allowance for that, and I will cover that later on also, because these are now covered in a fairly new code of practice, a Euro code, that covers this in situ assessment of concrete, right? So we make some allowance for that when we, especially when we are using the indirect tests, right? Okay, so now we go to interpretation. Now there are some slides which I have sort of like blanked out like this. That is because these things that they were done a bit earlier, Concrete Society Technical Report 11 BS 6089. So those days when you took cubes, you know, there was an idea about potential strength and actual strength. So we don't go to that anymore, but this is just in case, you know, you want to have a look at these slides. And typically potential strength means, you see, because the thing is you are comparing the concrete in the structure with concrete that has been delivered, right? So you cannot expect the sort of concrete grade to be the same in the structure as if as in the cube, because the cube is well cured and tested under lab condition, right? And we normally use a safety factor for that also. We know that the concrete strength in the structure you know, is something where the FCU value is divided by 1.5, right? Partial safety factor for materials, concrete materials. So if we get, say, let's say 3 cubes or whatever it is, right, from the structure, and this is a dispute about the concrete that has been supplied, that mean strength, this is those days, right? I mean, the new way of doing it is a bit different. I tell you that, right? So then the mean strength you multiply by 1.3, and that is called the potential strength. So if the potential strength is greater than the characteristic strength, we say the compliance is met. If it is less than 0.85 C, the compliance is not met. And in between, of course, there is some area of uncertainty, right? Okay, now this is a bit of a different scenario. This is the new Euro code, right? Now, first of all, they say that the in situ strength, now earlier we had this 1.3 thing, right? So here it is slightly different, right? So if you take 1 divided by 0.85, you don't get 1.3, you get some, maybe, well, I don't have a calculator, maybe something like 1.17. So this is a bit more conservative, right? Bit more conservative. And anyway, it also gives you a table. So now these are the standard grades, right? This is the standard grade, and depending on, you know, whether it is a cylinder or a cube, let us say that, okay, let's say this is grade 20 cylinder, grade 25 cube, right? This is the way that it's mentioned. So in situ, if you have, so you take 0.85 then, 85 of that. So the grade you expect in the structure is only 17 if it's a cylinder strength, or 21 if it's a cube strength, right? So that is used in the interpretation of these results. Okay. Right. So this is a bit of a what do you call it? A flow chart. I'm not going to go through this, but you know, there are 2 things which is called approach A and approach B. Now approach A. Now here, this is for old structures, right? And this is for a new structure because there is a dispute over the concrete quality. I'm not going to go into this because that's not so important and it's not very widely used, right? Like for precast concrete components, right? So in an old structure, you can either use cores or you can use a calibrated method, right? Now, if you use cores, you have something called approach A and approach B. Approach A means you are prepared to take 15 or more cores, right? Very few people want to do that. But I remember many years ago, we looked at the Putlam Cement Company, the buildings, there was a major renovation. I think we took a lot of cores there, but unfortunately this code was not available. So we did various other things. Now, if you have less cores, 3 to 14 cores, you can use approach B, but it will be more conservative, right? I mean, you can get a higher in situ grade if you use this. So if you spend more time and effort and money, then you can get a better result, right? If you use less time and effort and money, then you have to be a bit more careful, right? And then the estimated strength will be less typically than if you use this, right? So similarly, in a calibrated method also, we use alternative 1 and alternative 2 depending on the amount of, cores or whatever it is that are being used, right? And this last one is about dispute over concrete quality. I covered this the last time also, but I will cover it this time as well. So these are all the methods at a glance, right? At a glance. So let's see whether we can understand something from this, okay? So let us say that you have only cores, right? So this is approach A and this is approach B, right? So here, now here, this is the estimated in situ characteristic strength. So that's the way it's done if you're actually, looking at an older structure, right? You are not checking the grade, right? You are checking the grade only here, that is early age, right? So here, you take, typically something like this. And then here you have, if it is less than 15, you get the mean strength, in situ mean strength minus K. So K, of course, is a function of the number of cores that you have taken between 3 and 14, right? So if the number of cores is less, the K value will increase. Therefore, your estimated in situ strength will go down, right? Similarly, in situ strength is also something like that, right? And you can go through this procedure, and I will go through that little by little, right? This one also I will go through it in all these slides, but once again, I would like to highlight the objective here for older concrete is to estimate the in situ strength. The objective here is to estimate the objective here is to check whether the correct grade has been supplied, right? Okay, so this is the FCK, right? This is the actual FCK, right? And you want to see, okay, if you take a core or whatever it is, has this grade been achieved, right? And there is something here saying that where all of these are concerned, you should take the lower of this expression or the lowest in situ strength plus 4, right? So these are typically the kind of provisions that are given in the code, but I just want to take an overall view, right? I mean, if you want to actually do it, then you have to study the code carefully or ask a testing lab or something like that, right? So here we are. Now, if you have greater than or equal to 15 cores, you have to calculate what the mean in situ strength is, right? And deduct K2 times S, right? Because this is the mean. And then now we put 1.48 here rather than 1.64, which is what we use for a concrete supply, right? And of course, the in situ strength, the characteristic strength should be the lower of this one or this one, right? This S value, you can actually calculate the S value, right? Or if it is less than 2 MPa, you have to use 2 MPa, right? And the K2 value that is used is 1.48, right? Now, if you have less than 15 cores, so this formula are similar to what you have there. Once again, you find the mean strength, right? And you subtract. Now, the standard deviation is not there because there aren't enough cores in order to find the standard deviation. So depending on the number of cores that you take from between 3 to 14, your K value will be very high here, but less here, right? So this will be the computed in situ strength, right? Characteristic strength. But also, if the lowest strength plus 4 is smaller than this, then you have to take that one, right? So, like I have said before, if you take a less number of cores, because of these K values, the in situ strength will be underestimated, right? So, so it depends. I mean, you can take a fewer number of cores and get a smaller in situ strength, or you can take 15 cores and get a maybe better in situ strength. Depends on what you want, right? Okay, so this is an example, right? Let's say this example, how do we implement this? So this is not a cube test. This is a core from which you get an equivalent cube strength, right? So there's a way to convert that. I might be able to cover some of that also. So this is from the concrete equivalent in situ cube strength, right? The core is a cylinder, but you have to convert that to an equivalent in situ cube strength. So you have a series of results here. You can see there are only 7 results, right? This is the mean, right? The minimum is this, right? Out of all of these things, the minimum is that. Now, what is the in situ characteristic strength of this, right? So the in situ characteristic strength of this is the mean in situ strength, which is that minus 6, right? Now, where do I get 6 from? So if I go up there, n equals 7. So from 7 to 9, the K value will be 6, right? So 15.49 minus 0.49 minus 6 will give me 15.49, right? Okay. Or you can take this minimum and add 4 to this. There we are. FIS lowest plus 4, right? You get that one. But you must take the smaller of these two. Smaller of these two. So this is the one that you have to take, right? Now this is the in situ characteristic strength. So what is the grade? In situ characteristic strength divided by 0.85. Remember I told you about that 0.85 factor that is used in this EN, whatever number it is, 17 something, right? So this is the grade, right? So as you can see, well, you can use this grade in a calculation. I mean, if it is a building in midlife and then you want to, you want to estimate, what is, whether it can accommodate a change of use, right? So this, I mean, I don't know, if you have something like this, either you take this exact value or you say that it is grade 18 or grade 17.5. We cannot say it's grade 20, it's less than that, right? Okay, so this is how to get a in situ strength, in situ characteristic strength, and then convert it to a grade in case you want to use it in a design calculation, right? Now these are alternative tests, right? And sorry, indirect tests that are correlated with cores, right? So now there are these different kinds of tests that can be done, okay? Now here also for the correlation, of course, here in a sense, you have to have not 15 but 18 cores, right? So you have to have a large number of cores. So actually this is useful. So here, anyway, to do the correlation, we need 18 cores. So maybe not many people might be interested in doing this, right? This is where I finished, I think. So once again, you have to follow this, right? A similar thing as what we had earlier, right? Earlier, the minimum standard deviation was 2 MPa. Now it is made 3 MPa. But unfortunately, you have to get a regression, right? And you have to take what is called the lower 10% of strength. So I'll give you a real example in order to demonstrate that a bit later on, right? Okay, but this is what is mentioned in the code of practice, right? So let us say that, you have these different, measurements here. So let us say it is a rebound number or a velocity or a pull-out test force, right? And then you have the in situ strength that you get from the core, right? And then you can draw this correlation line, right? But what actually happens is that, there is already a standard line that is provided. There is a standard line that is provided. So what you do is you find the difference between this point and this standard line. So that is the deviation from this standard line. Okay. The standard line is drawn in a way that generally it will always be below the practical values that you get here, right? So you get these deviations and then you get the mean deviation. So when you get the mean deviation, what you do you're taking this standard line and you're shifting it upwards, right? Well, you can shift it downwards also, but like I said, the code of practice has given this standard line so that you know, generally it needs to be shifted up. Right now, when you shift it up, you get actually the correlation, the mean correlation between the in situ strength taken from a core and the non-destructive test, the indirect test that was carried out. But the code, because it's an indirect test, they want you to take what is called the you know, the 10% line. In other words, you must draw another line like this so that you know, between that line and another line 10% above, that will be a range of strength. So in other words, you don't take this mean correlation, you take one that is lower than that. And that amount that is lower is given by this expression here, right? I will try to give it in an example, but I think the example is a little distant away from this. But remember this concept. Okay, this is how you do the calibration. Okay. Right, now, before we get to that, I will just show you some, you know, straightforward things and, you know, these different types of, you know, indirect tests that are available, right? So in a rebound hammer, what you actually measure is surface hardness, right? You're not measuring the strength, right? Typically, you have to take 9 to 25 readings over an area of 300 square millimeters, 300 millimeters square, that is 300 by 300, right? Typically, people take about 12 readings. Right. So now this result is influenced by the hammer orientation, whether it is horizontally standard, but you can have vertically upwards, vertically downwards. So there will be things like age, surface carbonation, moisture condition, coarse aggregate type. All of these things will influence the calibration. That is why I am not happy when people say they have taken a rebound hammer set of rebound hammer readings, and they have used a calibration chart that is provided by the rebound hammer supplier. Okay, but all of these things will be different, right? So actually, you should try to ensure that the surface is dry, right? But then, of course, you have to look at things like how old the concrete is, right? What the coarse aggregate type is. Hammer orientation, the difference, of course, we can rely on what the rebound hammer supplier says. But everything else will be different, right? So now let me just give you some example. Now this is in the early days, many years ago, I think, when I just started off at Morocco University. You know, we did rebound number versus cube strength just to see. Now this is published in the Engineer, right? So you can see that the cube strength varies with the rebound number. Now it so happened that, you know, I thought you should have a straight line like this, right? You should have a straight line like this, right? Now I will show you what the Eurocode correlation is. It's not a straight line. But the other thing that I want to show here is, you know, we had some cubes that were wet and some cubes that were dry. That is in order to get a bit of a spread of strengths also. Now, this correlation line is drawn only between rebound number and cube strength for the dry cubes, right? Now, if you take the wet cubes, right? If you take the wet cubes, now they have a range of strengths, right? Range of strengths, but very small range in rebound number. And rebound number is fairly low also, right? So, which means that strength has no effect on the rebound number. So the story from this that I want to say is, if ever you are taking rebound hammer readings, you have to ensure that the surface is dry. Okay. If it is a wet surface, then the rebound number will only be a reflection of that wet surface, the hardness of which will be reduced. Okay, because of the moisture. Okay. Right. Okay. Now, here you do in fact find a straight line, right? In the what do you call it? In the Eurocode, right? There's a slight change here, the inclination changes slightly. So what we are doing is, if we are getting a correlation between rebound number and strength, right? What we have to do is we have to get that correlation using 18 cubes, right? And we have to find the difference between each one of those points and this line, right? So that we draw a line that is parallel to this. We cannot draw a straight line just using these points, right? You might think that, okay, we get a set of points here and we just draw a straight line through that. No, you cannot do that, right? The code forces you to maintain this slope, the shape, right? That is the idea behind the correlation between this indirect tests and the strength, right? So your age and your carbonation and all of those factors will be different. That's why it's encouraging you to do this correlation. But this shape is only shifted vertically by a set amount, right? This slope remains constant. This slope remains also constant, right? Now, where ultrasonic pulse velocity is concerned, right? Then you have these different things, and pass between two transducers. So the results are influenced by things like reinforcement and microcracking and moisture condition and things like that, right? And the moisture condition is very important, right? Now, those days, people thought that, the relationship between strength and this pulse velocity was given by this logarithmic expression, right? So pulse velocity is on a natural scale, cube strength is on a log scale, right? So this is from a very old paper, I think, not one of mine, right? So let us say that, you have, a wet cube strength here, right? And let us say that concrete gets put into a structure, right? So the actual core strength will be here. So there will be a drop in strength because, like I said, we cannot expect the strength in the concrete to be actually the strength that is in the lab, right? So there will be this drop in strength because of that, right? But separately, if you do a lab correlation, you will get something like that, right? And this loss is the pulse velocity difference from the strength loss. In other words, this is the what do you call it, the lab value, and this is the strength in the structure, right? So that pulse velocity loss is because of the change in strength. However, in the structure, now when you do the pulse velocity here, you are doing it under moist condition. So the pulse will travel fairly quickly through the moist concrete. In the structure, especially if it is something like 12 or 15 years old, right, you will have very old concrete, right? And I am assuming you're doing it when it's dry, right? So then, there will be a loss in the pulse velocity because of the desiccation, right? Because the water is not there compared to what you have here. So this is called the desiccation line. I think this is from a paper, early paper from a fellow called Thompson, right? Now, we actually did this. I think so. This is actually a structure that we investigated, right? So we tried to use, now those days we did not have this line. Okay, now this is the line. It is not really a logarithmic, it's a polynomial, right? But this is also not. But okay, so now let's go back to this, just to show you this effect, right? So this was a wet cube correlation. Separately in the lab, we also got a dry cube correlation like this. Now we got some pulse velocity and co-test results from the structure, right? So what we did is, in order to get this correlation line for the structure, well, those days we didn't take, I mean, now you are supposed to take 18 codes to get this correlation, right? So those days we would have taken maybe about 8 or 10 codes, right? So you have 8 or 10 strength readings and 8 or 10 pulse velocity readings. Now actually you can draw y equals mx plus c through that, right? But here we are maintaining this m the same as this m in order to make this parallel shift, right? And then you can get the optimum value of the intercept by doing a sum of squares thing or whatever, right? So what I'm trying to say is now actually the Eurocode gives you better guidance, right? It tells you for each of these correlation points, find the difference between this line, right? Then you get the mean of the line actually a bit lower than that, okay? I cannot entertain questions on these very detailed things, but hopefully things will get clearer, right? You know, when I do some examples, right? So like I said, so this is the basic curve, right? So when you get these correlation lines, you cannot move away from the shape of the basic curve. That is the main story here. And this is for the pull-out force, which we don't do very much, right? Okay. Right. Okay. Now, so I have, when I do the examples, I will give you examples of these various things, right? Now, this thing I covered in my earlier lecture also. If there is a dispute on cube test results, right? So if you have 15 or more core test data, once again, right? Then your in situ mean strength should be greater than or equal to 0.85 times characteristic strength. Let's say if it's a grade 25 concrete, and then you find the standard deviation from this, right? Then the in situ strength should be greater than or equal to this, greater than or equal to this value in order to accept the concrete, right? And in addition, the lowest in situ strength that you get should not be lower than this, right? Should not be lower than this. Then you can say, well, the concrete that was delivered by the supplier, in fact, has this FCK value, right? Now, suppose you have 15 or more indirect test data and 2 cores taken from the lowest strength areas, right? So what you do is you do, let us say, 15 rebound hammer tests, right? You take the 2 lowest rebound hammer values, take those areas, right? Take 2 cores, 1 each from those 2 areas, right? Then the lowest value of the in situ strength, right? That is the equivalent cube strength you get from the core should not be less than this, right? 0.85 times FCK minus 4, right? And if you have a very small batch of concrete, now it's debatable what a small batch is, right? Maybe if you have 1 truck, that is enough. So sometimes typically, you know, in these disputes, you find that the cubes from 1 truck has failed, right? Then if you have already made some notes on the site as to where that concrete went, okay, then you can take 2 cores from that, right? And then you say, you are not allowed to get the mean strength. You take the lowest strength must be greater than 0.85 times whatever grade you are supposed to achieve in the cubes. The grade you are supposed to achieve is 25, 0.85 times 21. So it's a fairly small value, right? It's a fairly small value. So this test actually is, what shall I say, a little bit comfortable for the concrete supplier and the contractor. Consultants sometimes don't like this very much, but it is there in the code, right? So the reason this is allowed is because of this statistical variation. I talked about that last time also, right? Okay, so you find that if you now I talked about last time, the compliance test is just FCU plus 3, right? Although the mean strength will be FCU plus 10, right? So if there's a batch with a low cube strength, you should not worry only about that batch, right? Because the overall concrete supply will be satisfactory. So that is why this target is not very difficult to achieve, right? So if you have a grade 30 concrete, right? The 30 minus 4 is 26, 0.85 of that is only something like 23 or something like that, or 22, right? So you know, provided your concrete is genuine, right? And the cube has failed because, you have not cast the cube properly or something like that, then this test is fairly easy to perform, right? But of course, if you have a widespread area where the cubes have failed, then you might have to go to something like that, right? Or even something like this. Okay. Right. Now I'm going to give you some examples, and these examples are wide ranging. So let's see whether we can finish. Okay. I don't know. I better not ask questions because there are a whole number of you, I think, who have joined, and then it will be not manageable. Right. Okay. So now this is the data obtained. So what is this first example? Yeah, this is scores taken from early life, right? Let us say the grade required is 25. So the cube test results, you have got only this, right? 22 to 22.8 MPa and 21.7 to 24.3 MPa, right? Yeah, two sets of results for some reason. I can't remember that now. Okay. Anyway, so even for a small supply of concrete, your average must be greater than 25, right? So which is not satisfying. Okay. I think I know what this is, right? I think this is, 3 cubes from one batch and 3 cubes from another batch, right? So this is the variation within each of those two batches, right? So the minimum should be greater than 0.85 times 25. Right? Okay. So that is a thing given in the SLSI, right? By the SLS standard, right? That the minimum should be greater than 0.85 times this. So this is the minimum. So all of these satisfy that, right? Each cube satisfies that. Okay. So that is okay, but this is not satisfied. So the person concerned, I had to advise the person to go for core tests, right? So he had taken many core tests, maybe more than is required, right? So all of these you get from the cores. So the mean you get is 19.9 MPa and the minimum is 18.0. Now this is, of course, if you are using potential strength, which is superseded. If you are using that, you take this multiplied by 1.3, 25.8, greater than 25, hence okay, right? Now, if you take the minimum strength required as per this EN, right, you take 25 minus 4 times 0.85, that is 17.9, right? So your minimum strength obtained here should be greater than this, right? And it is just greater than that, right? Okay. Actually, if you round this up, you will get 18. But anyway, so the minimum strength requirement is satisfied there. Okay. So then you say the in situ quality is grade 25. Okay. So what I'm trying to say here is that, this potential strength also gives sort of similar results to this EN, right? But now people generally don't use this potential strength method, right? Okay, I'm going the wrong way, right? So yeah, okay. So this is in summary, but I showed earlier as well, right? Now, if we look at core testing, these are some slides on core testing, right? So these are repeating sometimes what I said earlier. For approach A, you need more than 15 cores. Approach B, 3 to 14 cores. If you have a concrete dispute, at least 2 cores you will need, right? So minimum diameter of 100. So if your thickness of the slab is less than 100, then you have to use smaller diameter cores because your length over diameter ratio must be greater than 1. But if you use smaller diameter cores, your variability will increase. So generally you need more cores, right? Okay. So you can do visual examinations and things like that. And those days, once again, Concrete Society technical report required you to quantify these voids. You can still do that. I mean, that's good practice, right? So trimming and capping, this length upon diameter ratio should lie between this. Because we are converting to cube strength mostly, it is better if you have length upon diameter close to 1 but greater than 1, right? So you can either do trimming or capping, high alumina cement mortar or sulfur sand. I know people use, plaster of Paris sometimes, but then some of those you have to use these correction factors, right? So it is better that you get all of these results also, density, compression testing and all of that, because once you take a core, you are in a sense disturbing the structure. It would be a criminal waste not to get as much information from that core as possible. Okay, so I will tell you more information again. This is only about the concrete, but even more you can, right? Then this is just to indicate that, now when you test this in a compression testing machine, if you test, length upon diameter ratio equals 1, then you will get a higher strength because you have this triaxial effect. Like you are trying to push this concrete together, but the concrete will try to expand because of the Poisson effect. It is prevented from expanding by the friction with the platen here. So there is a lateral force that is set up like this, right? So because of that, this is concrete tested in a triaxial condition. Now, if you test length upon diameter equals 2, you get the same effect. But by the time you get to the center of this specimen, that triaxial effect would have disappeared. And therefore, we call this typically uniaxial strength, right? Anyway, because our course we are converting to equivalent cube strength, like I said, we typically use length upon diameter ratios slightly in excess of unity, right? There are ways to convert that in order to get the equivalent cube strength, right? Now, also the direction of drilling is important, right? Now, this would be if it is a vertically drilled specimen. Now, if it is a vertically drilled specimen and this is a horizontally drilled specimen, if you think about a column, right? Now, the concrete is poured into the column like this, right? And so if you take a horizontal core and you test the horizontal core like this, once again, when you are giving compression like this, due to the Poisson effect, it will try to move outwards like this. And these planes of concrete pouring will act as planes of weakness. So you will get a lower strength here than you get from here, right? So a horizontally drilled core for the same grade of concrete will have a lower strength than a vertically drilled core, right? So all of those things are covered in these different codes of practice, right? And this is for, correcting for embedded reinforcement and things like that. I'm not going to go into all of that, right? Okay, and I'm going to skip this also. And here, this lambda is the length upon diameter ratio, right? And so for a horizontally drilled core, this will give you the equivalent cube strength. And for a vertically drilled core, this will give you a, equivalent cube strength, right? So this is the actual strength of the core, which has a L upon D ratio of this. Lambda is length divided by diameter, right? And the actual strength will be obtained by using this formula for vertically drilled cores and this formula for horizontally drilled cores, right? Now, if you want 95% confidence limits, you can say it's plus or minus 12%, right? We don't really use those very much if you use cores directly, right? Right now, like I said, once you take a core, try to do all of these things in the core, because if you are doing an actual structural assessment, so by the time the structure is in midlife, you're not worried about the concrete quality and whether the contractor supplied you the correct concrete. You're worried about whether you can do some calculations and see whether this structure, which was normally used as an office building, if it is going to be used as, let us say, a storage area, whether, the concrete and the steel properties are sufficient for them, right? So, and then also you may be worried about durability. So you measure the depth of carbonation, measure the element thickness and the cover, right? So if you measure the element thickness, you can get an idea about the actual depth of the concrete, right? You may even with some judgment be able to reduce the partial safety factor for dead load, because you have now a very accurate estimate of the element thickness, right? But that requires some expert judgment, right? Ideally, if you are drilling a slab, say for a 12 or 15-year-old building, instead of avoiding the reinforcement, you should try to cut through a reinforcement, right? Because then you can take that little reinforcement piece out. You can do a small coupon on it and test the reinforcement strength, right? Because like I showed you in that earlier slide, the yield strength of the reinforcement has a big effect on the moment of resistance of the slab. Now, you should not cut any reinforcement if you are taking cores from a column or a beam. Ideally, you should not take cores from a column or a beam, right? Because in a column, you will be weakening the concrete. Like I said, concrete plays a big role in a column. And in a beam, of course, you may be able to take a core, but again, you must make sure you do not compromise the shear strength of the beam. You must try to avoid all reinforcement and take the core at the mid height of the beam and at the mid span also, because mid span there will be almost zero shear, right? If it's uniformly loaded, of course, right? Then you can try to do some ultrasonic pulse velocity tests before the coring for the calibration. So that so if you core it, that means you have to use some water to make sure that the cutting bit does not get overheated, right? If you use water, then your ultrasonic pulse velocity, the moisture condition will change, right? So it is always better to do the indirect test. If you are doing the correlations, even rebound hammer, you can correlate with cores. But the rebound hammer test and the ultrasonic pulse velocity test that you are doing at the same place where you are getting the core, you have to do that before you take the core, right? When you take the core, of course, that point will no longer be there for one thing. And for another thing, even a close by point will be compromised by the moisture, right? And there are these other tests also that can be done, right? So these are some tests for durability. I'm going to skip the ones that have no direct influence on in situ testing, right? But say cover to reinforcement, very important, right? In addition to information about durability, it will also tell you something about the lever arm of the slab or something like that, right? And also the cover to the reinforcement, the cover meter can be used to locate where the reinforcing bars are, right? Because once again, if you remember that first slide that I showed about that moment of resistance ratio, right? In fact, the bar diameter and the bar spacing have a big effect on the moment of resistance. So even if you use the correct yield strength, even if you use the correct bar diameter, instead of using spacing at 150 millimeters, if you have spaced at 175 millimeters, then the moment of resistance will reduce. And using a cover meter, you can get the spacing of the reinforcement, right? Okay, so depth of carbonation, also you have to spray as soon as you take the core on a freshly cut surface, which is a core surface. You have to get the depth of carbonation, right? So half cell potential, this is a particular piece of equipment that can be used. So this potential between this copper sulfate electrode and the reinforcement, right? So you have to connect it to this reinforcement like that, and depending on the potential, you have different chances of corrosion, right? Then you can do what is called a resistivity test, right? Here you supply a voltage and then you measure the amperage in that way, and then you can get what is called the resistivity in ohm centimeters. If it is less than this, corrosion rate will be very high. If it is greater than that, corrosion rate will be very low. So the basic thing for this is, if your concrete is very dry, and if you are confident that you can maintain it at that dry state, right, then even though your depth of carbonation has gone past the reinforcement, right, you don't have to worry so much, right, because the resistivity is low and the corrosion rate will be quite low. Okay. So these are some penetrability tests. I will skip that one, right? But these are some durability indices. Now this one I have already indicated to you, right? And these chloride levels and sulfate levels, this is if you are doing some chemical testing, right? So sometimes this is important for an existing structure, right? If you want to see, okay, what is the risk? Let us say a structure has been close to the coast for about 25-30 years. You can get at different depths, what the chloride level is, right? So up to 0.05% by weight of concrete is low risk, greater than 0.15% is high risk. And these are the values for sulfate, right? So this is the way that you get carbonation depth. So what actually happens is that Yeah, now the areas that remain colorless like this in a phenolphthalein solution, those are the areas that have got carbonated, right? These are uncarbonated areas, right? So when you're doing this carbonation test also, you have to be careful. Typically, you should, I think, have this specimen horizontal like this, because if you have it vertical, then this red dye, this, you know, this red coloration of the phenolphthalein will run into this area as well, and you will not be able to get a good measurement. Right. So these are based on some sort of results that we have taken over the years. Right. Okay. So we can do this water permeability test. That is not so much an in situ test, but that is more to approve the concrete before it is used. Right. So these are some results. Sorptivity we can do on the core itself. Right. But there isn't very much guidance on which sorptivity values are acceptable. Maybe there is more recent literature on this, but typically these are the values that we used to use earlier, right? I will not go into details of that, right? Full-scale load testing, you can have either in situ non-destructive tests, or, you know, if you can actually remove a member or precast members, you can, you know, test it to destruction. You should not carry it out before 28 days of age. You must have scaffolding both so that you can mount dial gauges, because the load testing is actually measuring load versus deflection, right? And also, by some chance, if there is a failure, then the scaffolding should be able to catch the elements with a minimum drop, right? When you read these gauges, it is better if you read them remotely using a telescope in case there is some kind of, you know, unforeseen accident. Right. So the objective is to ensure that the element is in the elastic range and ensure that the member experiences the required loading, right? So in other words, you know, if you are testing a beam, now there will be slab, you have to load the beam as well as the slabs on either side. Even if you don't load the slabs on either side, if you load a beam, you know, the slabs will take part of the load to the other beam. Right? So you need to be able to assess what is the actual load coming on that beam, right? Then when you are applying the load, right, you should what is called eliminate arching action, right? So for example, if you are using sandbags, right, you know sometimes the load may not go directly vertically, but it may arch across the sandbags like that, right? So there are various details. I can't be going into all of those details, right? So there are two kinds of approaches. So you can see whether the serviceability requirements are being satisfied. So then you just have the design dead load plus imposed load, and these are the acceptance criteria, right? Instantaneous deflection and instantaneous crack, right? If you want to get the design strength, then you use dead load plus 1.25 of imposed load, or 1.125 of dead load plus imposed load, right? So you apply the load and remove it incrementally, right? You have to do 2 tests with one hour in between, and you can consider even doing a third test with the load left for 24 hours. The acceptance criterion, the percentage recovery of the second cycle. No, so you have a loading and then you unload, right? So you get what is called the percentage recovery. So the percentage recovery after the second cycle should be at least equal to the first cycle, and it should be greater than 75%. The percentage recovery for RC and Class 3 PSC, and 85% for Class 1 and Class 2 PSC. So basically, you know, so if this is deflection and that is load, so you load it and then you unload it and see whether it is basically in the elastic range, right? That is why the recovery has to be at least 75%. Okay, right. And the other approach, of course, is to test for failure, but this is, of course, testing only typically things like precast concrete elements. Okay, right. Now, a few more case studies. I think this result I have already shown you. Right? Yes. Now, the rebound hammer, let me try to spend some time on the rebound hammer, because it is a test that many people want. It's an easy test to perform, provided you perform it in this comparative manner. Okay. In other words, comparing satisfactory and suspect concrete, right? So you had grade 30 concrete 4 months of age, grade 80 concrete 8 months of age, which is not very good because after 6 months, there sometimes is too much carbonation. Anyway, what we want to compare is suspect versus satisfactory. So for grade 30 also there was suspect and satisfactory, grade 40 also suspect and satisfactory. These were in different parts of the structure, right? So you have a list of suspect, different locations. So so these are different locations where you have satisfactory concrete and different locations where you have suspect concrete. You don't actually need the same number of readings either, right? But you need about, maybe typically 15 to 20 readings, right? Maybe you can manage with about 12. It just depends on, statistically whether, it makes sense, right? Here you have less because, less area with grade 40 concrete, right? So you get the means, then you get the standard deviations, then you get what is called the pooled, is it called variance or whatever, right? It's there in the next slide, right? Pooled sample variance, right? So SP squared is n minus 1 into S1 squared plus whatever, right? Then you calculate the t value, right? T value is this mean minus this mean, right? Satisfactory mean minus the suspect mean. Now, actually here, your satisfactory mean is less than the suspect mean, right? So then you're okay. Here, of course, your satisfactory mean is greater than the suspect mean. Now, the question is this difference statistically significant or not? That is what you want to do, right? So you get this pooled sample variance, and then you get what is called this t value, right? And here also you get that same t value. So for the t value is an indication of the difference of the means, right? Difference of the means, okay? Right, now, how to explain this? Now, this gives you different kinds of t values, but I will go here first, right? Now, in the first example, let's look at the second example, right? Second example, we found that the satisfactory mean was greater than the suspect mean. So now the suspect mean is lower, right? So now this is the one-tailed test. Now typically we assume that these differ, that they vary in this way. Okay. Now, if this, if the 5, so we say okay, 5% of those differences are allowed to be less than you're allowed to have 5% that does not fall within this acceptance region, right? So corresponding to that, there will be a particular t value here in that student's t-test distribution, right? In that first example, the suspect mean was actually greater than the satisfactory mean. So strictly speaking, we should do a test also and see whether they belong to the same population, right? So if you want that test to be carried out at what we call a 5% level of significance, right? So you have a t value here and a t value there, and it should lie in between that, right? So what we actually get is just a single t value, right? So it doesn't matter whether this comes out minus or plus, right? But you use a two-tailed test for this sort of thing and a one-tailed test for this kind of thing, right? So you find that the t value for a 5% level of significance is 2.04, right? I have not mentioned that here, but I think this must be for this must be for a two-tailed test, right? Because what you are saying is to see whether this is different from this. Here, what you are saying is to check whether this is less than, right? Okay. So for a 5% level of significance, this is the T value. Your T value is less than that, right? So what that means is you have a particular allowable T value there, right? And the T value that you have calculated falls below that, right? Between that, right? So it's okay, right? And similarly, if you go here, right, your T value is 1.36, right? Now at a 5% level of significance, your allowed T value is 1.717. So once again, it is less than, right? So once again, we find that this is less than that, but it is not different from this at a 5% level of significance. That's how we call it, right? Now, when you are comparing differences, if you take a 10% level of significance, right, then that is even a better pass rate, if you want, right? But it does not satisfy the 10% level of significance, right? It satisfies a 5% level of significance, right? So what I'm trying to say is, so if you want to have a 10% level of significance, then you know the margin that you have for deviation from this mean is very small, right? So 5% is the standard. If you want to show that there is no difference, right? Then you can use a higher level. So that's the way you do this hypothesis testing, right? Okay, right. So okay, I have put this down again on this slide. So the level of significance is the risk of a null difference being accepted as different. So if there is no difference, for it to be accepted as different, so a 10% level is a very high risk. 5% level of significance is an average risk, and a 1% level of significance is a very low risk. So if you want to demonstrate similarity, show that the T calculated less than T tables is at a 5 to 10% level of significance. To demonstrate a difference, show that the T calculated is greater than the T tables at a 1 to 5% level of significance, right? Okay, so let's go back to this. Now, instead of using a 5% level of significance, if you use a 1% level of significance, right? And if your calculated T value is even greater than that, right? So you can measure T from this way to that way, or T from that way to that way. We're not worried about the sign, right? So if your calculated T value even is beyond this 1%, it means that it's definitely different, right? It means that, you know, that there is definitely something wrong with the concrete. So the concrete is suspect, right? The reason why we say this is suspect and satisfactory is because the cube tests failed here, right? Here we are going into the structure to see whether the concrete in the structure, which is supposedly suspect, and the concrete in the structure, which is supposedly satisfactory, whether there is a difference between that or not, right? So this is the kind of way that you can use rebound hammer testing. The testing is fairly straightforward, easy to do, not much expense, right? The analysis is a bit complicated, and you have to get your head around that analysis, right? Okay. When you're doing it, of course, you have to make sure that both the satisfactory and suspect area, of course, you have to definitely test. The comparative satisfactory area must be of a similar age and, of course, similar grade to the suspect concrete, right? Okay, this is everything that I described earlier in words, right? So I'm not going into that, right? And this is another comparison of that nature. So, okay, right. Now I'm going into another area, which is midlife assessment. Okay, so this is where change of ownership is concerned, no design details. There were various strategies that were used, and actually the findings were that the column strength was a bit low on 2 floors, and we found some input values for, I think, design checking that was done by the State Engineering Corporation. But anyway, so these are the cores. So these are the typical kind of values that you can get, right? This is the depth of the top plaster, bottom plaster, the actual concrete slab. So you can see the variation of concrete slab thicknesses. Then the carbonation, cover to steel, if we have drilled and cut through the steel, right? Then of course the pulse velocity, and all of these things you can get from cores, right? So some of the statistics that we got, you know, the mean and standard deviation for slab thickness, concrete cover, depth of carbonation, yield strength of the steel from the steel that was cut, percentage elongation and things like that. And then, you know, using some of the methods available at that time of this new Eurocode, the estimated cube strength for the cores, and then this is for the columns. Now the columns, of course, I think we did not take cores. We used ultrasonic pulse velocity and correlated it with the cores that we got from the slabs. Okay, right. Right. Okay. Right now, this is something that I highlighted earlier. So this is the pulse velocity here. I gave you this method, right? This is the equivalent cube strength. So this is for correlation. Normally we need 18 cores for correlation, but I'm just going to manage with these 6 for purposes of explanation, right? So this is the mean, this is the minimum, right? And if we want to get from these cube strengths alone, you know, this is the same one that we had earlier, and this is the grade that was estimated, right? Now, we are trying to test a much wider area using pulse velocity, and we are trying to get a correlation between these cube strengths and pulse velocity taken at the same locations, right? Now, first I want to say that, you know, I am just demonstrating a simple correlation between this and this, right? Using this, what do you call it, polynomial recommended in the what do you call it, Eurocode, and using this logarithmic relationship, which I said was used earlier, right? So it'd be difficult to get these R-squared values are not very good, but at least you get a slightly better R-squared value for this polynomial compared to this logarithmic one, right? So basically I'm agreeing with the Eurocode, even though this is something that we used earlier, right? Of course, both of these are better than, no, actually this is better. This is a simple linear regression, right? But anyway, let's stick with this polynomial. Okay. So what we do is, now this is the equation given in the Eurocode, right? So we take these, right, and we convert the strength, we convert the strength to this using this equation that is given in the Eurocode, right? Okay. Then this will actually give the predicted strengths using this curve, using this basic curve. That's a basic curve, right? Now, the actual strengths are these, right? So you take F actual minus F predict. These are almost all positive, right? Because this curve tends to be a, you know, give you low strengths, right? So then you take the mean of that, which is 15.67, right? So then what you do is you take this 15.67 and you okay. So 15.7, right? So this 15.7 has to be added to this because the others are, of course, X values. So this 990, you add 15.67, roughly 15.7. So then that will get you to 1005.7. So these are the different points, but we assume that this is the correlation curve, right? Okay. Now, if you just curve, you will, you know, a parabolic curve like that, you will get different values and different, you know, coefficients here, right? But you're not allowed to do that. You have to put this factor there and that factor there, because that it is only that will make it parallel to this basic curve, right? So you get this difference and you do it, but then again, you have to, from that, you reduce this one here, right? So actually, I will not go into that, right? But from that, there is a way that you take, that standard deviation and reduce it to this actual correlation curve which you get here, right? So it is all given in the code of practice, right? And with a little bit of thought and care, you can get there, right? Okay. Getting close to the end. So this is the condition assessment for a 70-year-old building. I'm just telling you the different kinds of tests, right? Giving you a flavor of the different kinds of tests. Now here also you get carbonation at the top and carbonation at the bottom. This is just to highlight that in most structures, carbonation at the bottom will be greater. And these are some other properties that were done. Sorptivity, I said if the sorptivity is less than 1 millimeter per square root of hour, then it's generally okay, right? Okay. And this is how you do the sorptivity test. You have a sponge here. You heat this for 250 degrees centigrade for 3 days, and you calculate the amount of water absorbed into that, semi-dry specimen, not completely dry, right? But dry to a standardized sort of condition, right? Okay. Now this is I have not explored this in great detail, right? But very often the top of the concrete, has a thicker rendering. The bottom of the concrete has, only a small sort of soffit plaster, right? So in order for the concrete to get carbonated from the top, all of this rendering also has to get carbonated. Separately, most of the slab is probably in sagging mode like that, right? And therefore, at the midspan of this slab, you find that, this is in tension, and the chances are that something in tension, we will allow sort of, what shall I say, external agents to penetrate more easily. This is just a theory, right? Okay. But typically, you will find that, the carbonation depths are greater at the bottom of these concrete slabs. Okay. Yeah, so in this particular project, we found that carbonation exceeded the cover. Significant corrosion was present only in moist areas. That is typically areas that you have to be particularly careful of, toilets and perimeter corridors. So very often what you have to do is you might have to do some repairs there, waterproof it, and try to keep it dry, right? Under all situations, right? Now this is a 100-year-old structure. Now before I talk about this structure, we had an external examiner at Moratuwa called Professor Tim Maibel, and he has written an article in the Structural Engineer Journal called "Nothing is Better Than Something." Right? I think most of us will think that something is better than nothing. He has written a very provocative article called "Nothing is Better Than Something." Now, that is because he and many other structural engineers like him are very concerned about the carbon contributions by the industry, carbon dioxide emissions, right? So he is suggesting to structural engineers, you try to keep these old structures going, do not demolish them. Because if you demolish, that means you have to put up a new structure, right? And while doing that, try to maintain your structural engineering practice as well. So you have to think a bit carefully about what kind of value you have for clients, even if you are telling them not to demolish and reconstruct, right? Okay. So it's a bit of a challenge for structural engineers. Anyway, speaking for myself personally, also, I like these older buildings. I think they add to a cultural heritage and things like that. So as far as possible, it's better to try and maintain them, right? So these are various tests that we did, right? So you can see these chlorides. So chlorides, if it is below 0.05%, then it's not so bad, and only one is sort of compromised, right? This is in the Colombo Fort, so not too far from the coast, right? Now these carbonation values, you can see, they are a bit high, they're not low, right? Okay, and compared to oops. I'm not sure about the cover values. I don't have cover values, right? I think these would be exceeding the cover, right? You normally don't get such high covers, right? But we need both. So this half cell potential and resistivity, right? So half cell potential varied between these two numbers, and here it varied between these two numbers. And I think if it is negative, I think I had that slide earlier on, then the risk of corrosion is not so great. Resistivity is certainly greater than 20 kilo ohm centimeters, right? So once again, probably because the slabs are quite dry, right? And so basically we gave a recommendation not to demolish the structure. The question here was, is it safe? Do we need to demolish this, right? Okay. So, okay, the findings: depth of carbonation exceeds the cover. Depth of carbonation is greater in dry areas. Now, that is also something interesting about carbonation. You know, structures will carbonate faster if it is dry, right? But you know, if it is wet, then of course, you know, you will find conditions suitable for corrosion, because that moisture enables the formation of a corrosion component, right? Chloride levels are not high. Half cell potentials are greater than this minus 350, resistivity greater than this. And therefore, you know, basically we said, okay, you can still keep the structure. I think this is the last section I have on fire damage, right? So sometimes it's a bit difficult to do these assessments. You know, a lot of times you have to use some judgment. There is some guidance given, I think, in a Concrete Society technical report, which I may have mentioned here later on, right? But I will show you just some of the things that we have used, right? So here, you know, you can get a visual idea about the degree of cracking and crazing, right? So this is medium and high. Percentage of reinforced exposed, right? Once again, low, medium, and high. And this is the average rebound number. So the rebound number gives an idea about whether, you know, there is likely to be spalling, right? Because if it's a low rebound number, that means the slab is hollow, okay? So based on, you know, an examination of these different conditions, right? For each of those panels, there was some kind of recommendation that was given, right? So D means demolition reconstruct. So we had 1, 2, 3, maybe 4, or only 3. Yeah, 1, 2, 3, 4 to demolition reconstruct. The ones with C to expose the reinforcement, right? So if you look here, percentage of reinforcement exposed, you know, you have low, 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 and here you have high, 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 and high. So mostly based on that, we decided that these two were these and these were L's. Now, none of these other things have reinforcement exposed, right? Okay. So you have to use a little bit of judgment, and these are the different kinds of methods available to just wire brush it, chip the surface, and then, you know, reinstate it, expose the reinforcement, and use, you know, repair mortar, here demolition reconstruct. Okay. This gives you some visuals. This is plaster crazing. This is actually concrete flaking. This is crazing in the concrete, and this is the concrete spalling. So you go from, you know, this is only the plaster, the concrete inside is okay. Here the concrete itself is crazing, meaning crazing means a lot of small fine cracks like this. Here the concrete has flaked off, and here the concrete has actually spalled off, right? So this is another case. Sometimes you get a pinkish surface, right? You have reinforcement exposed in a large area like this. Beam edge has spalled, and the reinforcement has deformed like this, right? Probably because of the heating, right? The concrete has got chipped away. This reinforcement is trying to expand because of the heat, but it can't, and therefore it sort of bends like that. Okay, right. Okay, so these are some of these levels of damage and repair given by this, right? So now, actually, in this particular field, I mean, I have done some work in the past, and you know, anything that I said about the Eurocode is quite up to date. But some of these other things, you know, there may be more recent versions of these technical reports and things like that, right? but the principles are similar, right? Okay, so I think I will stop there. I will stop there, and maybe I don't know whether I should stop sharing, but I will stop and I will entertain questions. You know, is somebody going to? Do I just look at the chat for the questions or what? Okay, no, maybe I have to stop sharing this. Right, so far there is nothing on the chat. Maybe you can even unmute yourself and ask questions because there are so many people who seem to be.
Professor, many members asked, is it possibility to deliver your presentation for their future reference? Is it possible to share?
Yes, I can send. Yeah, you mean this PowerPoint?
PowerPoint presentation. I saw some messages in the chat box. They asked the today presentation. So I asked our engineers to put their email addresses in the chat box. Then we can deliver with, if you are agree.
No, no, I can't do that. Shall I send it to Lalit? Is that okay?
Yeah, okay. Right.
Yeah.
Thank you, sir.
Right. Right. Okay. So there is a question. Co-testing, is it destructive testing or non-destructive? Okay, that's a sort of. I think sometimes people used to call it a partially destructive test, right? Because it does destroy the concrete, right? But destructive typically means testing to failure. So in that sense, it's non-destructive. But sometimes people use the word partially destructive test. Yeah. Okay, everybody's sending their email addresses and no one is asking questions. So I will leave it to the organizers. That means Lalit. Yes. Okay, there's just okay. I don't know now. There are some of these. As per BSEN chloride limit recommendation by cement content, how can we predict concrete content? Yes, that is correct. Yes. So typically, I mean, you can get the cement content in the concrete and do it, but a rule of thumb is to multiply this by 6. So 0.05% will mean 0.3% by weight of cement, 0.3% by weight of cement, right? But sometimes people allow up to 0.4% by weight of cement, right? So you can check what the BS says. Yeah. Is it necessary to do carbonation test for indoor concrete elements? Yeah, so I think the background to that is to ask whether, since indoor concrete elements tend not to be moist, whether we need to worry about that. So maybe you don't need to worry about it, but typically, why we do these tests is that there is going to be a change of use. So the new user probably, wants to have a fairly comprehensive sort of assessment of the structure. So then, you would do then carbonation testing as well as other kinds of testing, on indoor as well as indoor elements, because some of the indoor elements can be moist elements like toilets, right? So then you should have a check on that as well. how to select the places in the elements to cut the core. So like I said, if it is a beam, you must select the midpoint of the beam and the mid height so that you don't compromise the shear strength and you try to avoid reinforcement. Okay. In a slab, I mean, you can do it at midspan. It doesn't really matter because, and also in a slab, if you cut the reinforcement, it doesn't really matter because there are a lot of reinforcement. So you're not going to compromise the strength very much, right? I mean, you're not going to cut. I mean, in one panel, you should not take more than one core, right? Okay. Is there any effect on the plaster for the cover of concrete? Can we reduce the cover by applying a plaster? Yes. Now, actually, in that book that I have written in one of the earlier versions, also I have said that maybe you can use reduced covers by applying a plaster because but you have to use some judgment a bit. I don't think you should reduce cover by more than 5 millimeters. And the plaster has to be a good quality plaster because if you're not careful, sometimes these mortars are mixed with a water cement ratio of close to 1, right? Which of course is not acceptable. I think you should then of course use a plaster with some kind of mortar plasticizer or something like that. So the water cement ratio does not exceed something like 0.6 or something at least. For fire damaged buildings, what are the suitable testing methods to evaluate the rebar and concrete conditions? Yes. So concrete, of course, typically we do these visual inspections and then we knock out the concrete that gets knocked out. Where the reinforcement is concerned, there is sometimes a bit of a concern, especially if the fire damaged building is, after firefighting, you might have a hot concrete hot steel element that has been suddenly quenched. So then you will find that the strength increases significantly, but the ductility reduces, right? So so fire damage is something that there are a lot of issues regarding, and you have to be a bit careful, but try and remember some of these fundamental ideas, okay? And maybe have a look at some specialist literature as well. Yeah. The rebar, once it has been heated and gone back, then the strength is not going to be any less than what it was before. But the ductility might be less. The concrete, if you heat it to only about 300 degrees centigrade, actually the strength will improve. But then beyond that, and due to cooling and things like that, the concrete might be compromised. So you have to just knock out the weak concrete. Okay, so Ajit Tambu has asked, columns are more critical elements than beams and slabs for concrete. Absolutely correct. Then what is a better way to assess the concrete or reinforcement of columns to check bearing capacity? Yes, so if you, so in an overall scheme, to do some comparative, I mean, this is just my opinion, right? Comparative, indirect tests, let's say something like pulse velocity, right? Do some pulse velocity tests and core tests on slabs, so that you can get your correlation. Then of course you have to assume that the concrete in the columns is the same as the concrete in the slabs, which may not be unreasonable, but which may be unreasonable also because columns are concrete as separated to the slabs. But then you can try to use that correlation to estimate the strength of the concrete in the columns. That's one way of doing it. I mean, if it is especially just, something like a 250 by 250 column or 300 by 300 column, getting 100 millimeter core is a bit not advisable. Yeah. Okay. But that's a good question. That's a good question. What are the penetration limits as per DIN 1048? Penetration, that is at water penetration. I think sort of 25 millimeters or 50 millimeters, but there isn't much guidance on that. there isn't much guidance on that. You know, the test method is explained, so that actually depends on the specifier, on the consultant. So maybe if you're asking what the penetration should be, I am not 100% sure, but you know, something like 25 to 50 millimeters. I think I have put that in the slide also. Maybe okay. What kind of recommendation for a carbonated soffit? So carbonated soffit, ideally to keep dry and don't worry too much about it, right? I think recently at Society of Structural Engineers also, there was a Japanese professor who was giving some talk, and I think he said the more important condition is the moisture level for concrete spalling, different types of structures. That was a kind of a field survey. Yeah. Okay, is it correct to mix testing of EN with the building design with BS 811 not from the point of view of stringent execution standards expected in EN design series? Well, I mean, you can argue about things like this, but I think it's okay. I mean, you know, the EN guide for testing for assessment of structures, there was nothing comparable to that in the British standard. While coring, if we cut through reinforcements, what will the following action to close the hole? So for a slab, of course, we assume that it's okay. And for others, we should not cut through the reinforcement. If we do, then I don't know. You might have to do something like welding. Welding is not advisable, but it's better than, you know, having a gap in the reinforcement if it's for a beam or a column. Can the rebound hammer test be done on curved surfaces? I suppose yes, but it may be difficult to. It has to be perpendicular to the surface. So that I'm not sure about. Is there any correlation between core strength results and rebound hammer test results? Yes, presumably there will be. Yes, that is why you are doing that correlation, right? If you want to then use rebound hammer later on to test other areas. At which point can we come to a conclusion to demolish the structure? Yeah, I suppose if there is excessive spalling, I mean, you know, and especially if the vertical elements are compromised, right? Generally, horizontal elements you can do something about it, but if the vertical elements are compromised, then maybe you can consider demolition. But there are a lot of other considerations also for demolition. Sometimes people don't want to demolish because reconstruction involves, you know, satisfying, you know, more recent zoning regulations, which may be difficult to do. So there are a variety of issues like that. Determination of diffusion coefficient of chloride is important for durability assessment. Well, this diffusion coefficient of chloride, maybe you can do that at the design stage, so that you try to estimate at you know, in how many years the chloride level comes to that 0.05 or whatever it is at the level of the reinforcement. There are various guidelines given also to estimate the diffusion coefficient based on you know, the water cement ratio and the percentage of porcelain materials. You will find that in the literature, right? There is a software called Life 365, and if you want, you can have a look at that, and that will give you some idea. How to convert core test results to cube test results? Well, I have given you some formulas earlier in the presentation, so you can have a look at that. Earthquake resistance assessment, in particular with old heritage buildings. Earthquake resistance, well, of course, the thing is, it would be difficult to do that, because to be earthquake resistant, your detailing also has to be earthquake resistant. So you might have to use some judgment regarding that. Best location to introduce a construction joint. This is zero shear or zero bending moment, right? So my understanding that it is typically zero shear, because the construction joint will still transmit bending, but not so much shear. Load testing on column. I'm not sure how easy it is to do a load testing on a column, because column will carry a large amount of load, and to apply that load may be quite difficult. Is it okay to have test result curves below the basic curve given in this? It's okay, but probably you will not get it. There is a Swiss company who presents new methods for repairing concretes, introducing new chemicals and repairing methods. And they introduce different products of carbon fiber also. Are you recommending strengthening by carbon fiber? Okay, carbon fiber strengthening is done. Right? My colleague, Dr. Now she's Professor Kumari Gamage, she's the expert on that. There may be other experts also. But there are some companies that do it. Okay, somebody is asking for a recording. The recording should be available on the IESL website. Strain measurements and continuous monitoring. Right. Okay, I did mention that. Yes. So yes, that is correct. So this is mostly a presentation on concrete. So that is structural health assessment, right? So there are people who are experts on that also. I think Dr. Levangam and Morotua does that. I'm sure people at Peradeniya also do it. I'm not sure anywhere else. So I think Professor Ranjit Disanayak used to do it. I mean, there must be others at Peradeniya doing it also now. Ranjit is quite busy nowadays, yes. If the cube test result obtained as 0.86 FCK shall be allowed without further test. No, you can't have 0.86 FPA. That is sort of, if you have 3 cube test results, for a small area, the mean should be greater than the FCK, but no single result should be less than 0.85 FCK. Okay, I think I have covered all the questions. My answers may not have been as satisfactory as you wanted, but any relation between carbonation risk and type used concrete, that is PLC and OPC. So I of course promote this fly ash, but fly ash has higher carbonation rates, especially at early ages. But I think the answer is not to avoid fly ash, but to cure it better. So to have at least 7 days of wet curing if possible. I'm not sure about Portland limestone cement. I'm not sure about the carbonation performance of that. Okay. Some people are wishing me happy retirement also. I think it's time to stop this presentation. Okay. Shall I hand over to Lalit?
Yeah, thank you very much. Actually, as you said, we are not going to retire this industry. That's why we organize this one also. Anyway, thank you very much, sir. Engineer Chamida Jaising, our deputy chairman, will be final conclusion. Engineer Chamida, over to you.
Okay, thank you, Engineer Lalit. First of all, thank you very much, Professor Priandayas, accepting our invitation and did a great presentation, and it's a very valuable and informative presentation for civil engineering industry. Dear sir, we refer your research papers, textbooks, and many materials at large while we are doing complicated structures. Therefore, you have done very big service to engineering education during your service period. If you retire from the academic activities from the university, I think your service is needed for industry many more years, especially in the civil engineering in the field. Therefore, I think you can't stop sharing your knowledge and experience. We hope your service many more years as an engineering institute of engineers, as well as other organizations will expect your services many more years. As Engineer Lalit mentioned, your service is very vast. Yes, normally in a physical platform, we are arranging some token of appreciation, but in this situation, we can't arrange. Therefore, we have arranged a small gift as a token of appreciation. We will deliver it very soon. Sir, once again, thank you very much for your participation and did a great presentation. In addition to that, today there is a large audience. I think there are many experts in the industry who have participated for this today presentation. So thank you very much for all the members who participated today presentation. There is a small announcement. I think this is our final event for the year 2021. The end of on this remark, we are finish our terms for the year 2020 as a civil engineering sectional committee. During the period, most of the seminars we organized by online platforms due to the present situation. Therefore, I must thank to especially the Chairman Civil Engineering Sectional Committee, Engineer Lalit Pallegama, Deputy team leaders, and the committee members and IESL staff, and especially IT department, Mr. Chamila and his team. You all did a great job during the throughout the our year 2021 term period. So finally, I thank all of you participate today, and I think the next session will start immediately. Again, thank you, Professor, your support, and I concluded today's session, and stay safe and good night. Thank you.